All right, let's take a look at the normal distribution, and in this segment, let's calculate some actual probabilities. All right, here's an example. Wine manufacturers are very cognizant of the extraction force required to open a corked bottle of wine. It's considered an industry standard for the average force to be 305 newtons, with a standard deviation of 28 newtons. A bottle requiring less than 240 newtons will not be sealed tight enough, and a bottle requiring more than 378 newtons will be too tight for most consumers to comfortably open. A newton is just a measurement of force. It actually equals 1 kilogram meter per second squared. Assuming the distribution of force is distributed normally, find the following probabilities. Now, before we actually find the probabilities, I want to talk a little bit about notation. If I use x as my random variable, I will say x is distributed, that's a little tilde, n for normal, and what will follow is always the mean and the variance. This is an ordered pair. Whenever we use this notation, everybody in the world that knows anything about data analysis will look at this and look at these numbers and say the first number is the mean, the second number is the variance. So for this particular example, I would say x is distributed normal. The mean was 305. Standard deviation was 28, but that last number has got to be the variance, so I'm going to square it. Now, anybody look at this that knows anything about data analysis? Let me fix that 5. That 5 doesn't look, matter of fact, that 0 doesn't look very good either. So let me fix this. This is 305. Anybody that knows anything about data analysis knows that this first number, this guy right here, that's the mean. That's mu. This guy right here is the variance. That's sigma squared. That's known. It's a standard. It's an ordered pair. Everybody understands that using that notation. Okay, first thing we want to do is find the probability a randomly selected bottle of wine will require too much force to open, then would be considered comfortable for the average consumer. Now, too much force means more than 378 newtons. So my probability statement would be probability that x, my random variable, is greater than 378. Now, if I wanted to, I could make this greater than or equal to. That doesn't really matter, because in the previous segment, remember we said that the probability of exactly 378 is 0. So adding 378 to this won't make a difference. So when I'm talking about a continuous distribution, it doesn't really matter if I say strictly greater than or greater than or equal to. It doesn't change the probability. But it has a big influence or a big impact on the probabilities if we're working with a binomial. So keep those separate. Because remember, binomial is discrete, normal is continuous. Now, the first thing you want to do is draw a picture. So my picture is going to be a normal curve. The mean, right down the middle, is 305. 378 is up here someplace. It doesn't really matter where I put this. It's just for illustration purposes. Help me figure out what I'm going to do. And the area I want is the probability. So this blue area I shaded in will represent the probability of 378 or more. Now, in your calculator, we will use a normal CDF command. It will be normal CDF, and the syntax is the lower bound, followed by the upper bound, followed by the mean, followed by the standard deviation. Now, when we go to calculator in a minute and do this, you'll see there's a normal PDF and a normal CDF. You will never, ever, ever use normal PDF in this class. There's no use for it at all in this course. The normal PDF does not give you what you think if you're thinking about a binomial. A binomial PDF gives you the probability of exactly 9 successes in 13 trials with pi equal to whatever. But remember we said earlier the probability of x equal exactly something in a normal distribution is 0. The normal PDF actually gives you the height of the normal curve at a specific value of x, which is useful for drawing normal curves in your calculator, but you won't have a need for that. So you will never, ever, ever in this course have a need for normal PDF. You just won't do it. Everything that we will be doing, all the probabilities we'll calculate based on the normal distribution, you can use CDF for. Now, for this particular example, the lower bound is going to be 378. The upper bound, well, where does this stop? Well, it goes to infinity. Now, obviously, you're thinking, no, wait a minute. You can't have a bottle that has that requires 15 billion newtons to open it. So why am I going out that far? This is based on probabilities. The entire normal curve, we use the entire curve because the curve, in terms of probabilities, fits what we're trying to model very well. Now, very, very quickly, when we get out here, in terms of probabilities, we don't get out here very far before we're almost zero. It's very, 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 very little probability. So we're not going to cut off and say, well, I think 400 is the most reasonable, so I'm going to go 378 to 400. No, go 378 to infinity. It's more accurate in terms of probabilities. How do we tell our calculator to go to infinity? Well, I will show you in a moment, but we use scientific notation, and that is E99. And there's a specific series of keystrokes that I will walk you through to get the right E here. This is not just any old E. The calculator needs to make sure that it understands, or you need to make sure the calculator understands you're talking about E99. That's scientific notation for 10 to the 99th. When you do that, the calculator goes, oh, they mean infinity, and it does its thing. Because here there's a lower upper. The mean here is 305 in this example, and the standard deviation is 28. It's a good idea. I didn't do it here, but I really should have before I started this. I should have reminded myself what the distribution is. It's normal, means 305. The variance is 28 squared. If the variance is 28 squared, square root of 28 squared is 28. Hence, there's the standard deviation. Okay, let's go to the calculator and take a look at that now. If I go to second distribution, just like I did when I was working with the binomials, I'll see the first two options. Option 1 is normal PDF. Option 2 is normal CDF. Never use option 1. Forget that's even in the calculator. Option 2, normal CDF. I'll select it. Lower bound was 378. Upper bound was E99. Let me zoom out of this for a second so you can see the keystrokes better. Okay, look above the comma key, and you're going to see a double E. It's two uppercase E's. That's the scientific notation. If we're on an 84, it's going to be in blue. The 83s will be in yellow. So press the second key and then the comma key, and that will give you a small uppercase E. That's what we use for scientific notation. Let me zoom back in now that we have that. There we go. Now 99. So that's 10 to the 99th. The mean was 305, and the standard deviation was 28. Lower bound, upper bound, mean, standard deviation. Hit enter. And that probability is 0.0046. So this is equal to 0.0046. That's how much area is under the curve. Remember, the total area under the curve is 1. Okay, next example. Find the probability a randomly selected bottle of wine will not be sealed tightly enough. Again, I'm going to just remind myself of the distribution. It's normal with a mean of 305, and the variance is 28 squared. Now, the probability statement is going to be a probability that x is less than, is it 240? Is that correct? I better go back and check. Yep, 240 newtons was the borderline or the boundary. If it's less than 240, we're saying it wasn't sealed tight enough. So I want to know probability x is less than 240. Or again, if you want, less than or equal to, it doesn't make any difference. I will draw my picture. The mean's 305. 240 is down here someplace. Doesn't really matter where. Shade it in. This is what I'm looking for. Here I'm going to start at negative infinity and come up to 240. So I will use normal CDF. Negative infinity will be negative E99. The upper bound's 240. The mean is 305, and again, the standard deviation is 28. So, in my calculators, I use the negative key, which if you look down at the bottom, you'll see a negative in parentheses. That's the negative key. That makes a negative number. The minus sign on the right-hand side is actually subtraction. Your calculator differentiates between those two operations. So let's take a look. I'm going to clear this, go back to second distribution, normal CDF, option 2. Hit the negative key, then E99, representing negative infinity, up to 240. 305 is the mean. Standard deviation is 28. Hit enter, and it's 0.0101. Now, I'm going to show you something kind of cool. Hit the program key. It's right below the stat key. It's PRGM. And go down until you see a program called shade norm. Now, these are made available to you by your instructor. If you don't have it in your calculator, contact your instructor. There may be a reason. The instructor may not want you to use these programs. But if your instructor allows it, run this program, hit enter. It says PRGM shade norm. That means shade normal. Hit enter again to run it. It's going to ask you for the mean. Well, that's 305. Standard deviation was 28. What's the lower bound? Well, I'm going to go with negative E99. What's the upper bound? 240. See, what it did is to make it the normal curve, and it shaded it in here. This is the area that got shaded in. That's where the 240 would be, with a mean of 305, and the area is 0.0101. Isn't that what we just got them saying? That's the same thing, right? Yeah, of course it was. Kind of a cool little program. Again, we said that this equals to 0.0101. That's the area under the curve. Okay, what's next here? Find the probability a randomly selected bottle of wine will require exactly 320 newtons to open. Okay, that's saying what's the probability x equals 320. Remember, this is a normal curve, so that's easy. That's 0. If you draw a picture, here's 305, 320 is up here somewhere, and that's it. There's nothing to shade. This probability is right here. We talked about that earlier. It's going to be 0 every time. It's going to be 0. If you put that in your calculator, if you don't believe me, you want to check it, you do normal, CDF. The lower bound is 320. The upper bound is 320. The mean's 305. Standard deviation is 28. So there you go. Try it in your calculator. I'm not going to do it here. Try it in your calculator if you want to double check me, and you will get 0. That won't be approximately 0. That really is truly 0. Okay, find the probability a randomly selected bottle of wine will require between 240 and 378. So this is the same probability that 240 is less than or equal to x, which is less than or equal to 378. Whoops, 378. Again, I want to draw a picture, because the picture helps me figure out what's going on. As a matter of fact, for my students, I've been known in the past to actually give partial credit for a problem that was done wrong, but they drew the right picture. I'm not saying your professor is going to do that, and I'm not going to say I'm going to do that all the time either, but, you know, it could happen. Okay, here's 240. Here's 378. Between 240 and 378, so this is asking for this area right here. This would be normal CDF. The lower bound's 240, upper bound is 378. The mean is 305. The standard deviation is 28. Oh, by the way, for my students, if you're actually taking this course from me, this is what I require. I require to see this command that tells me exactly what you did. This is showing your work. I'm also going to need to see what the distribution is, which we said was normal with these parameters. Picture's a good idea. Okay, let's go to the calculator and find that probability. So I'm going to go to distribution, normal CDF, lower bound's 240, upper is 378, the mean was 305, and the standard deviation was 28. Hit enter, it's 0.9853. Now if I run that program again, that shade normal program, it's kind of cool. Means 305. Standard deviation is 28. The lower bound was, what was it, 240? Upper bound was 378. Hit that guy. It's going to take a second to draw. And see this area here, before when we did, this area was shaded in. Now it's open. And all this is shaded in. Again, it's 0.9853. This equals 0.9853. That's the area under the curve there. Okay, next is based on the information provided, what percent of wine bottles are either not sealed tight enough or sealed too tightly? Well, again, I'm going to remind myself of the distribution. And the probability statement. This is saying the probability that x is less than 240 or less than or equal, plus the probability that x is greater than or equal to 378. Because remember, 240 or less it wasn't sealed tight enough, and above 378 it was sealed too tight. Well, if I draw my picture, the mean's still 305. 240 is down here someplace. 378 is up here. And what it's really asking for is this tail plus this tail. I need to add those two probabilities. So I can do these as two individual normal CDFs and add them up. Or I could recognize the fact that the whole curve is 1. So if I take 1 and subtract off the piece I don't want, which is right here, I could write this as 1 minus the probability that 240 is less than or equal to x, which is less than or equal to 378. Which in your calculator would be 1 minus norm CDF, 240, 378, 305, 28. Which we just did that middle piece, and we found that was what was it, 9853? So I know this could be 1 minus 0.9853. Whoops, 53. So if you do that, well, let's go ahead and do it. Let's go to calculator and take a look at that real quick. What we're really asking for here is I want this area and I want this area. So I'm really trying to get out of this. Okay, so I'm going to take 1 minus second distribution, normal CDF, 240 to 378, with a mean of 305 and a standard deviation of 28, and 0.0147. So I know this is 0.0147. That's how much area is combined in these tails. Now, one common interpretation of these probabilities is the percent or the proportion of the population that has this characteristic. So based on this information, we're going to say a little more than 1%. Almost 1.5% of all the bottles are either not sealed tight enough or it's too tight based on the industry standards, which means a little more than 98% are good. They're in that range that we feel good about. Okay, I want to repeat problem number 2, the second one that we looked at, by converting values to a standard normal, then computing the probability. Now, something about a standard normal. Remember a standard normal, we normally use z to represent a standard normal. Z is normal with a mean of 0, standard deviation of 1. Now, we also use what's known as a z-score. A z-score is equal to an observed value, something that you observed happen, minus the mean from that distribution divided by the standard deviation. A z-score is actually the number of standard deviations an object is above or below the mean. If it's a negative value, you're below the mean. If it's above a positive value, it's above the mean. So, find the probability a randomly selected bottle of wine will not be sealed tightly enough by converting to a standard normal first. Well, not tight enough was 240, right? So z is going to equal 240 minus the mean, which is 305, divided by 28. I'm going to grab my calculator because I don't know what that number is off the top of my head. Let's see, 240 minus 305 divide by 28. This is a negative 2.3214. Remember, z-score is the number of standard deviations an object is below the mean. That's a little more than 2 standard deviations, almost 2.5 standard deviations below the mean. Now, remember before we talked about the empirical rule? We said if it's mound-shaped, which the Bell distribution is, the mound shape comes from the normal curve, anything beyond 2 standard deviations is getting pretty unlikely. Matter of fact, if we go 1 standard deviation, 2 standard deviations, we have about 95%, which means no more than 5% left over for the tails. It's symmetric, so no more than 2.5% in each tail. I don't know what this probability is going to be off the top of my head. Yeah, you do. We already calculated it. It's going to be 0.01 something or other. I don't recall what it was. It's going to be, it's up here someplace. Where was that guy? There it is. It should be that. Because all we did is we transform it to a standard normal, so I should get the exact same value. But using logic, I know it's going to be less than 2.5%. It's going to be less than 0.025. Okay, so if I draw my picture, what's the mean? It's 0. It's a standard normal. Where am I looking for? Negative 2.3214. I'm looking for this area right here. So I would use normal CDF. Lower bound is negative E99, negative infinity, up to negative 2.3214, mean 0, standard deviation is 1. Let's go to calculator and see if that actually works out. Within rounding, we know that it will. It's possible because of rounding we may be off like in the thousands or 10,000s, place something like that. So negative E99 to negative 2.3214. Oops, let me adjust that. There we go. Negative 2.3214. The mean 0. Standard deviation is 1. Negative E99, negative infinity to negative 2.3214, 0, 1. That should be 0.0101. It is. When we transform a non-standard to a standard normal, and we calculate probabilities, the area is the same. We're just transforming. We're just basically changing the dimensions on it or something. It's no big deal. Okay, use probabilities from the standard normal distribution to verify the empirical rule. I'm not going to work through all this, but I'm going to show you how. The standard normal is Z. And we say Z is distributed normal 0, 1. Well, if I draw the picture for the first piece, the empirical rule says if I go one standard deviation from the mean, and because the z-score is the number of standard deviations, so between negative 1 and 1, this should be approximately 0.68. Correct? So you go normal, CDF, negative 1 to 1, 0, 1. And you go find that's approximately 0.68. It's 0.68 something or other. The next one would be, if we go 2 standard deviations from the mean, that'd be negative 2 to 2. If we look at this area, we know that's about 95%, right? That's from the empirical rule. Well, do the same thing, normal CDF, only this time from negative 2 to 2, 0, 1. And you're going to get about 95%. And I'll let you figure out 3 standard deviations, the same idea. If you calculate those and compare them with what we remember, love, and adore from the standard normal, you can say, wow, yeah, that's where it comes from. Okay, I think in the last section I'm going to do here, in the next video, so we'll take a look at finding percentiles using